ask about formalism for arithmetic quantum field?
Yeah. So I guess in this talk I'll kind of try and give a vague overview of kind of what are quantum field theories without going into the physics too much, or pretty much at all, because I don't understand the physics much, and kind of explain what is an arithmetic version of all of that. And by that I mean some theory which looks at, instead of space-time, at p-adic fields or number fields, and kind of studies something like physical systems on them. So I guess so maybe first of all is from the physics point of view, so field theory, or a quantum field theory, so we have some maybe some space-time manifold, and on that space-time manifold we're interested in what's called a field over it. So one example of fields is some principal G bundle on it. So we have this principal. So these are physical fields on M, and this should be kind of thought of as when you choose a specific type of G, then you get back some type of physics out of it. So one can study some classical mechanics, for example, and then on this thing you also have a notion of states, which is some global sections of this space of fields. This would be some states on the physical I will not give any concrete examples, but vaguely what all these ideas are is a way to organize, or kind of more generally think if these are a way to organize principles from physics, and maybe to make a more mathematical rigorous way of thinking of all of this. So HUJI 88 suggested some more rigorous way of thinking of all of this, and he suggested an axiomatic way, which is a topological quantum field theory is a function from some category of cobordisms to vector spaces. And what do I mean by that? And all it does is that for any n-dimensional manifold, any closed, and we associate a vector space Z of epsilon, and for any n+1 dimensional manifold M with boundary of M being equal to some disjoint union of two n-dimensional manifolds, and we associate them up from one vector space to the other. And so we just say here, so the category of cobordisms from this kind of point of view is, and for any, there's a category where the objects are n-dimensional manifolds, and the morphisms are n+1 dimensional manifold, and so morphisms from one into the other is n, which has a boundary between this discrete union.
Two questions.
Yes.
First of all, are the manifolds oriented or not necessarily?
So now they are oriented, but later I will kind of describe how you can forget about the orientations,
Okay,
because I care.
And what if you replace the roles of sigma 1 and sigma 0? I mean, what do you mean by
So for now they
boundary
are
of M is sigma 1, disjoint union sigma 0 star? What do you mean by the
as
star?
a sort of star. I mean, so yeah, now I do orient things, and so this I just mean inverse orientation.
But, okay, and suppose now you reverse the orientations on both, then the ZM becomes the dual.
The
of
dual.
the-
Yes. So reversing orientations takes you to the dual vector space.
So that's part of the axioms for the fountain.
Yeah, so yeah, I'm kind of hiding some of the details behind here, but from kind of maybe the physics point of view, is we think of the boundaries as some space manifold, and then we want to kind of study what happens to states on this type, on like say a single particle over some flow of time, and so that's kind of where this whole concept comes from. And kind of maybe one important thing from this point of view of quantum field theories is that we think of certain manifolds as morphisms rather than kind of as topological objects.
So in this picture I should think about as time being a two-dimensional manifold?
No, so time is the dimension of going from one boundary to the other, and then space is the boundaries of it. So this kind of specific example would be like some model of states on, say, particles, and here you have like a single particle which over time splits into two particles. But this is kind of very hand-wavy, especially because I don't really understand the physics of all of this. So we have all of this, and there have also been, and also this theory is a topological theory as opposed to some more general quantum field theories, where here we only care kind of about the topology of the space-time, but not about the actual complex structure, symplectic structure, and all of it. The reason why we have arithmetic in all of this is, well, it's ideas of the ideas of arithmetic topology, going back to Maser, Reznikov, Kramer, Rishita, but Maser kind of was the first one to point this out, and these are have some analogies between arithmetic objects and topological objects. And under this analogy, we have that a number field can be thought of as some three-manifold primes as some link L inside of this manifold, periodic fields as surfaces, kind of under this finite fields on a circle. And kind of the ideas of these analogies come from duality theories which exist in arithmetics. For example, classical theory can be thought of as some sort of three-dimensional or two-dimensional Poincare duality. On now, instead of regular topology, on some étale topology side, or kind of just on the absolute Galois group of the field. I'll kind of not go too much into this, but it was then suggested by Min-Young Kim suggested in his work about arithmetic Chern-Simons theory to apply the tools from Tiki of T's to these new manifolds. So we have a bunch of kind of specific examples of quantum field theories. For example, you choose some group and you look at G bundles on your manifold. So one can ask himself, okay, can I now look at some notion of G bundles on a number field or on the periodic field and kind of try and then rediscover some of the nice invariants which come from specific quantum field theories, and to get some new invariants or new ways of looking at known invariants in number theory. For example, in some recent work from this year of So, kind of under this also analogy, one can look at, say, a curve over a periodic field as some four-dimensional object, or over a finite field as some three-dimensional object. But using this type of ideas, so. Kind of So, for example, they explained how to think of Langlands. I think there they did just a geometric Langlands, but from certain Chern-Simons theories, you can get some Alexander polynomials of naught, which under this analogy should correspond to periodic L functions. And so again, one would hope that maybe if you have this nice theory, you can give a new way of describing periodic L functions and functions in general. But kind of all of these constructions have been taking a specific known example in physics and trying to kind of really describe everything in the realm of arithmetic. And so in a recent joint work with So with the joint work with Arnold and Massat, we explain some axiomatic formalism kind of similar to Attia's. Which takes values on both arithmetic and topological objects. So instead of just kind of constructing this one vector space that has been in the theory so far, we define a cobordism category containing both the topology and the arithmetics, and then study functors on that. In dimension 1 plus 1, I'll explain why I write 1 plus 1 and not 2. We classify our TQFTs in terms of Frobenius algebras plus extra structure, which I will get to later. And what do I mean by this, and why should one expect them to be classified by Frobenius algebras? Or what are Frobenius algebras? Well, for the classical quantum field theories, one has a classification that 1 plus 1 dimensional quantum field theories are equivalent to just regular Frobenius algebras. And where does this come from? Well, the idea is if I'm given some, so a 1 plus 1 dimensional thing, by that I mean that my objects are one-dimensional manifolds, so just a collection of circles, and morphisms are surfaces having such boundaries. And so now, due to the functoriality of all this ideas, if I want to, once I know what the vector space of one manifold is, then I know what the vector space is for all the other manifolds by the functoriality. And so TQFT assigns just some vector space Z of the circle. And then I need to study what are the morphisms, but now if I take a surface, then I can cut it down into pairs of tangents. And so now for this, then I will get that actually to understand my quantum field theory, it's enough to understand its values on the following objects. So this can be thought of as the map from a vector space into V tensor V. This is a map from V tensor V into V. This is the map from the empty set into one component. So this would be a map from C into V. This would be a map from V into C. And so this is kind of a structure for Frobenius algebra. It's some vector space which has some multiplication, co-multiplication, a unit and a co-unit. And kind of the power of this is that if I construct this vector space in a very specific way, or more generally for this, such a manifold, then I get a map from C into C. In other words, this would associate just some number. But this number can be calculated by calculating the variance of these very simple objects. And so now we would kind of just have to first compute stuff on pairs of tangents and then use some combinatorics to see how things glue together. The nice thing is, we also get that kind of to cut periodic fields to also pairs of tangents.
So I don't understand, this description by Frobenius algebras is only in 2 dimensions.
Yeah, so for now only in 2 dimensions.
But
so
why is the intuition because periodic fields are cohomologically of dimension 2?
Yes. Yeah, in a moment I'll actually explain in more details what category that I'm working on. But if I have this, once we do have such a cobordism, and we can still describe it in terms of Frobenius algebras, then that would mean that if I want to compute certain invariants on periodic fields, then I can actually cut it down to computing invariants on actual topological pairs of tangents, or maybe some pre-completion of them, but still. And actually from this, you get a formula which was already discovered by Yamagishi, but using very algebraic tools. But now, using this ideas, we get a formula for the amount of extensions of a periodic field K, and with Galois group gamma. So we fix some like finite P group, and we can actually get formulas for how many field extensions have that given Galois group. And the hope is to kind of later be able to also generalize this to study certain volumes on moduli spaces of representations, or kind of more general, but kind of just in this very simple setup we managed to also do this. Any questions before I get into the actual construction?
Is there a reason why periodics are the analog of surfaces?
Well, kind of from looking at their absolute Galois group and the cohomological properties of that, but kind of this category that I work with are certain groups with a Poincare duality.
Well, but this is connected to the muscular group?
Yes. Yeah. So I only explained the classification in kind of dimension 2, but then looking in dimension 3 as well, these same definitions of cobordism categories also work for certain nice Galois groups of number fields which have some three-dimensional duality. Okay, so yeah, this is exactly related to Mischling groups. So to be able to kind of study these objects at the same time, and because we only care about the topology of the objects, and instead of looking at surfaces, we move to look at their fundamental groups. And so there's various ways to think of duality groups, but maybe kind of the simple way is, so we would focus on duality groups in the world of pro-P groups. And so G, a pro-P group, has a Poincare duality which I would denote by PDN group over FP over ZP. If the dimension of the group homology with FP coefficients is finite for every I less or equal to n, and the dimension of Hn and of P is equal to 1, and there exists some, the cut product induces some non-degenerate bilinear pairing from Hi to Hn minus I to Hn. And kind of this definition is equivalent to something which is maybe closer to the usual Poincare duality, is that there is some I this is a module representing and we have that this I actually induces a duality from and some group homology, which I will not get into. But it induces some of something like the usual graduality, but now on group cohomology instead of the one coming from geometry. And maybe kind of
I have
Mhm.
a question. So in QP, should we be thinking about like a subgroup or a quotient of the Gauss group?
of what?
Well, I mean, Gauss group QP is not for P.
Yeah, so I'm taking the maximum Propi quotient
Propi,
now.
okay.
Yeah. Well, one could also work with maximum Celos subgroup, then you'll have like some infinite genus. I mean, it still has a duality, but it's kind of like infinitely generated. So maybe a few reasons why. Okay. So yeah, before I go into the reasons for all of this, I will say one more thing: is that by relative group cohomology theory, which is due to and why do I care about some relative group cohomology? Because I want to talk about, well, objects with a boundary. And so we also have a notion of a relative concurrent-duality pair, which is G together with S, PDN pair, where this is a collection of closed subgroups of G, which I like.
Finite collection?
A priori, for the definition of like relative cohomology and so on, you don't need it to be a finite collection, but actually for pro-P groups, if they do have concurrent duality, then it will show by Wilks that the collection has to be finite. But we do allow kind of counting the same subgroup a few times, and maybe kind of an important theorem, which I think was also by Bailey and Ekman, is that, or at least one of the steps in this direction, is that over Z, so just discrete groups with a regular duality, TB2 pairs always come from geometry, and actually this was later used to show that PB2 groups are pi1 of some surface. And by come from geometry here, I mean that this is pi1 of some surface with boundary. And here, these are pi1, the collection of the pi1s of connected components of the boundary of this manifold. Some surface with boundary and this is so kind of the most simple example would be kind of this a pair of pants. So the group pair that we associate to this will be the free group on two generators, and then the subgroups will be a group generated by A, a group generated by B, and a group generated by A times B. So we have these three groups, or We do also allow multiplicity, so the cylinder will just be a group together with the group twice. So these were kind of the.
I think it's a fundamental not following. So what does it mean PDN pair?
So a PDN pair is a group together with a collection of closed subgroups on it, such that the relative group homology, which I will not define, but is the one that makes the long exact sequence where you take the homology of D and relative homology of S, this relative homology has a punctuality on it. But the nice thing is, at least in dimension 2, which we'll focus about today, there is a complete classification of such things also for pro-P groups. So I'll write down an actual presentation and relation.
Is some kind of connection between punctuality for different subgroups also in definition, or?
What do you mean? Sorry?
Well, for different elements in S.
Oh, so yeah, one kind of implication is if GS is PDN pair, then every group in S is a PDN minus 1 group. This kind of also follows from some diagram chasing. But that would mean that if we take in our cobordism degree PDN minus 1 groups to be the objects, and then morphisms will be pairs such that they map into this, and that's kind of a category that we want to work with. And how does this relate to periodic fields? And this goes back to the Mushkin. So if we have K over QP, let's assume for now P isn't equal to 2 just because it's easier. And we have that the degree of K over QP is n. The pth roots of unity to the power of r are contained in K, but the p to the r plus 1 roots of unity are not contained in this field K. Then the maximal pro-P quotient of the absolute Garo group of K is a PD2 group, and it is isomorphic as a pro-P group to a group generated by x1, y1, xn divided by 2 plus 1. 2 plus 1, so by
so R is at least 1.
So R is at least 1. Yeah. If we don't assume that, then we get a free group, but actually one more thing that I want to suggest here is to think of it not as a free group, but rather as a relative duality group relative to the maximum 10 extension. And so then it's some punctured torus or something, if you don't have this. Yeah. Having a single relation so what do we have here? We have that the maximal pro-P quotient of the absolute Garo group is something generated by n plus 1 generators with a single relation, which at least mod p to the r is exactly relation that you get for a surface of genus n divided by 2 plus 1, and outside of it you have this kind of extra twist. And it's also true that any Poincare duality, Pro-P Poincare duality group in dimension 2 will have such a nice presentation. And what about Poincare duality pairs? So G. So if we assume that S now is non-empty, then GS is a PE2 pair. If S is equal to some collection S0, S1 until SB, G is free Pro-P on 2n plus b generators. These generators are x1, y1, xn, yn, s1 until sb. We have some self-generators like this with S0 being equal to the following word. And then at the end we multiply by all these boundaries. And so these groups, this is the group generated by the element S0, this is the group element generated by the element S1. And everything here is actually in groupoids because you want to work up to conjugation. But kind of this type of writing boundary components of a surface is exactly what you would get also in the topological setting. You only get this kind of extra twist in the Pro-P world.
What is GKP? It's the Galois group of what? All the extensions of
degree P.
All the extensions of degree P.
Yeah. So this is the
But with this condition on the roots of unity, yeah?
Yes. So if you don't have this, if it's also not in K, then generators, where here it was a group generated by n plus 2 generators. So you do also kind of get something similar to this, but it kind of kills one of the generators because you have this kind of extra. Yeah. So kind of this is the realm where we suggest working with cobordisms. As this classification is due to Gareth Wilkes of PD2s, and then well, now we want to talk about what happens when we glue such objects and what we mean by all of this. So here I kind of don't talk about orientations, but there is also a way to talk about kind of orientations, and there is also a notion of some orientation character. But one more thing that we get in the Pro-P worlds is
So in practice for p-adic fields, where do you get the S's from? I mean, they are the analogs of punctures in the surface, but where do you get them in the
So a priori, you only kind of could potentially get it here, where you talk about the maximal Tain extension, and then that will kind of, the P part of that will give you only a single boundary. But kind of another way of thinking about it, which follows from what I did in my thesis, is when you want to take a p-adic field and cut it down into the Galois group in two parts. So actually what I do is I take this Garo group, I cut it down over ZP B, and now I take the fixed field of these subgroups A and B, and so I get some kind of very big infinite extensions. And
Right,
these
but
would be
there's no way to describe them using ramification theory or something, except for this example that you gave. I mean, they're just arbitrary, relatively small closed subgroups of the whole power group, right?
yeah, they're infinite index.
Yeah,
kind of
infinite,
thing.
yeah,
But no, you can describe them in terms of like very kind of specific extensions that come, for example, from taking all P roots, I think, of like, or like from taking certain elements of the units of your field.
Like,
extension. Yeah, I think like taking, maybe that would just be the Abelian part, so maybe you need to take some, yeah, but if you look at like specific ways of looking at the presentation, then you could kind of say what things you're adding. In the Abelianization, it would just be some like Kummer extension, I think, but outside of that, it's slightly more complicated. But yeah, I don't have a fully nice way yet to look at these here. But what we do get is, at least in the global setting, the boundaries will come from looking at the maximum unramified outside of self-primes, where the self-primes will now be the boundaries. So at least in the global setting, I kind of have a nicer description of all of this. Kind of orientations in discrete. This is a choice of generators. So this is just plus minus 1. Entropy. We look at ZP star, and so now we have kind of many more choices of orientations, which is kind of a new feature that you would get from this theory. So what I mean by that, well, the kind of top cohomology is isomorphic now not to Z but to ZP, and so yeah, choosing this kind of isomorphism for a generator gives me kind of many more choices. What else did I want to say? Oh yeah. So maybe one way to deal with non-oriented manifolds, because these things are only orientable mod P to the R, but their boundaries are always orientable. And so such non-oriented TQFTs, one way to think about them is we take some manifold, we choose orientations here on the boundaries, and this will be non-oriented. So I'm allowing non-orientation preserving homeomorphisms of my bigger manifold, but not of the boundaries. Or one more way to think of this is in the language of co-spans. So I have some group G, I have some subgroups of it S1 and S2, and I care about how they sit inside of G, and not just, but I'm allowing kind of to let them sit in different ways. Okay, and now what about gluing? So if I glue two things, this is exactly taking a push out in this category of co-spans, or taking an amalgamated product. So say I had kind of two manifolds or two kind of bigger manifolds which have some way of identifying their boundaries. And the way of gluing them in this category will exactly be kind of the cosine, and this would be the amalgamated product of S2 of H, or more generally you can describe it in terms of some graph of groups where you join the different components if you had more than one component that you glue together. Or yeah, because geometrically it's back. And then in a previous work of mine that I did in my thesis, I described here's a nice descriptions of all ways to cut ZP scriptings of concurrent duality group of dimension 2. And using this nice classification, we were able to show that organisms have this nice classification. So maybe let me say more precisely. So for us, we have our category of cobordisms of dimension n are so objects are finite collections of concurrent duality groups of dimension n, and morphisms between some u and n to collections are groups G together with morphisms from U and N into G, such that we have this phi of U and phi of N. G relative to the images is P n plus 1 here. And these morphisms are defined up to equivalence, where the equivalence is if I have another group and an isomorphism making this thing commutative, then I say that this morphism is equivalent to this morphism. So that's a category of cobordisms, and then a TQ of T will again just be a functor from this category into another category. But the nice thing is, from the classification of Wilks, we actually get that a PD1 plus 1 pair is classified by n u r g by 4 numbers, where this is the size of n, this is the size of u, this is the orientation level, and this is the the rank of G minus the size of n minus the size of u minus 1.
So, Nadav, you didn't say it explicitly, but it seems that PD1s are always cyclic or procyclic.
Sorry.
Yeah.
Yes. So
And okay, so all the groups that interfere
Yeah.
in these collections,
So
in the 1 plus 1 case would be. Would be
PD1 are just collections of ZPs. Yes, so we have a bunch of collections of ZPs, and we have these nice invariants, and now by careful studying of kind of how can you take a PD2 pair with such invariants and cut it down using amalgams into smaller pieces, you can always cut it down into a pair of bands. And you also have a kind of complete classification of what are all the relations that can be done by different ways of gluing pairs of hands to get the same group.
What is it? In the Mushkin group, the relation of the Mushkin group is not exactly Fuchsian.
Yes, so now we also take the push outs in the category of pro-P groups,
Yeah, of course.
which allows for kind of more.
No, but can you describe geometrically the splittings of these PD2 groups in the pro-P category from the geometric picture of whatever corresponds to the Mushkin group?
Yes, but you kind of have more exotic ways of gluing the things, so you can also take just like a discrete group, which will still be kind of a hyperbolic group with like a weird relation from these extra gluings.
No, but look, if you just think about the Mushkin group, just a relation discretely, it's possible to describe all its splittings.
Yes, but now you need to take a family of different discrete groups to get all the possible ZP splittings of the Mushkin group, and this comes from the fact that actually something if you have R prime greater or equal to R, then this thing is still a Mushkin group.
Is this a Mushkin group?
Yes. I mean, it's kind of equivalent, it's isomorphic as a pro-P group to this one.
Oh, really?
So you also need to include discrete groups with such things. And if you include kind of all these higher powers, then you do actually get all things. And so this maybe kind of, the thing of it is, if you take something non-oriented mod R and non-oriented mod R prime, then when you glue them, you get something non-oriented mod the minimum.
But is it true that every splitting of the discrete group will give a splitting of the in the pro-P? What's that?
If you take all these different discrete groups. Oh yeah, every splitting of the discrete groups.
I think it's true in the pro-P completion of the circle.
Yeah, no, I'm pretty sure it's also true here. Or at least I have a nice family of splittings of the discrete group which do all complete, which do all give ZP. I'm not sure what are all the Z splittings of the discrete group, but I know that.
This is described by the gesture of this group, so it has a gesture.
Hmm?
It's described by the gesture of the group. Of those.
Yeah, no, I just didn't write them down to check, but I think it should give you everything.
But there's someone I think who proved that for pro-P completion of a surface group, all the splittings of the pro-P completion of the surface group in the pro-P category
Yes.
comes all from the discrete.
Yes, so this was a work of Gareth Wilkes, and he did it just for surfaces, and then in my thesis, part of the work that I did was to extend this to all the Mushkin groups in kind of very similar type of manner. But yeah, up to automorphisms of your Mushkin group, you can always move the splitting into a very certain form, and then take a Z splitting of a discrete group and show that it completes to a ZP splitting. Yes. So they all come, and you have a kind of complete description. And kind of, I was told I need to do a short break.
About now.
But the pro-P completion of the surface group is not the PD2 group, according to what you said.
Of
Pro-P completion of the surface group, the discrete surface group,
yes.
is not the PD2 group.
Why not?
I thought you wrote all the.
Oh, sorry. I when I take R to be infinity, it's this thing I just find, and this is just a way of notation. Sorry. And so also here, if I take R prime to be infinity, then it just disappears.
Okay.
Yes, so they are. It's just, yeah, sorry, it's just.
Take like a few minute break, so everyone who wants to leave can leave. Okay, I think everyone went to leave from further left.
Sure. Yeah. So, yeah, so kind of the last few things that I wanted to say a bit more is, first of all, what is this extra structure that you get in the Frobenius algebra? And then what type of TQFT will actually give you this counting of Galois extensions. So, first of all, I want to show kind of that any such thing can be given by pairs of hands, and so kind of the way to do this is you start with a bunch of n circles. To each one you do group theoretically, you join this a bunch of steps of adding pairs of hands, each time reducing the amount of boundary components when you glue.
But this has nothing to do with the Mushkin now, they're just surfaces. This has nothing to do with the Mushkin now.
Now it's just surfaces, but in a moment I'll glue in things which will make it also a general Mushkin. So first, I just glue all of these to get some compordism, like pro-P versions of these, but still everything will work. And now to this, what I glue is I glue a bunch of tori, again kind of just regular tori. But then in the end, what I glue is this thing which is some p to the r, some Demushkin group with a p to the r. So the group on generators.
Why do you single out Torah? Before that you just said, why do you consider Torah as a building block?
Oh, so after that I actually decomposed the torus into two pairs of hands, but just for the simplicity now. So yeah, the torus will just be the thing generated by x, y, and s1, the free group, together with the subgroups. And where here, this will be the thing generated by s1, and here it will be the thing generated by x, y, s1. And then I add this special group, which will be, again, x, y, s1. Here we again have s1, but here we will have some x to the p to the r, s1. And so this will kind of be in charge of all this non-orientability. And then you again do kind of the symmetric thing of here, so you get a map from, and if you check how many generators this group has, and this will exactly give you, so here you get
So
some,
where is the non-orientability here?
here in this component, because one of its boundary component is xp to the r, xy, s1. So this word is not a it's
not a Fuchsian thing. It's not.
so by non-orientable, what I mean is that the group action on H2GZP is non-trivial. And from this you get what's called an orientation character, which is a map from G into opt ZP. And so when this map is trivial, then I call my group orientable. And kind of in a similar manner to the trivial orientation character. And when it's not, then it's non-orientable. And this is kind of says how what is it still trivial. So I have this thing, and then this can be further cut down into two pairs of hands. And kind of the, this is kind of where the extra axioms in the Frobenius algebra come from. Whereas if I glue both of these in an orientation compatible way, so either both preserving, both reversing, or up to some ZP star element, then I will get such a thing. But then if this one, so suppose I have this is A, this is B, this is AB, this is C, this is D, and this is C, D. If I take A to C, but B goes to D to the alpha, where alpha is 1 plus P to the R ZP, so it's a unit sitting inside the this R part, then the resulting thing that you get will be exactly something non-oriented mod P to the R. And so this gives you kind of this way of flowing, and you also get something similar to what you get in geometry, where if you glue two Klein bottles, then this is the same as gluing a Klein bottle to a torus. So here as well, if I have something which is non-oriented mod P to the R, and I glue it to something which is non-oriented mod P to the R prime, then the resulting thing will be the same as gluing a torus to the minimum. So P to the min of R prime. So you can only make something less oriented when you glue it. You cannot kind of make something suddenly orientable if it's already locally not. And then you have kind of one more axiom which comes from something similar to a Mobius band, where if you have a punctured Mobius band, I don't know how to draw a Mobius band, so I'll just draw a circle. But if I have a puncture here and I reverse the orientation on this puncture, then by going kind of around it, I can get back to the other orientation. So kind of twisting the orientation on a boundary component doesn't change what happens if you're in something non-oriented. So that's kind of the main components, and these are kind of the three axioms which are written more carefully later, but using all of this now we get that we can actually decompose things. Okay, and so now one final thing that I want to say is what an example of a specific TTFT and what it gives us about Nadav groups. So this comes from what's known as a Digraph-Witten theory, and where here we take a gamma, some finite P group. We consider principal G bundles over gamma on some manifold. So at least topologically, what this will be, if it's a classifying space, if it's a k pi 1, then this will be morphic from pi 1 epsilon to gamma mod conjugation. And so for our boundary components, our vector space, so Z of ZP will be equal to maps from ZP into, say, C. We get it to be a C vector space, or in other words, this would just be the C vector space spanned by the different elements of this principal G bundles, which this is isomorphic to just the gamma mod conjugation, because gamma is this P group. So this is finite dimensional and everything is nice. And then more generally, by some pull back, push forward of G bundles, we can get, if we have some relative thing, we can get Z of it to be the map from one boundary component to another. But more concretely, what this will be the Z of G will be a map from Z of N to Z of U, which takes an element, a principal bundle on U, and returns the complex number equal to some, this is P2, so this is just the size of the centralizer of the element of gamma. Yeah, so we basically what we want is we want principal G bundles on G, so homomorphisms from my bigger group, which restrict to a specific homomorphism on my given closed subgroups. And it takes, so I'll not get too much into the details of this, but what we do get is these very nice formulas that if we want to compute what these maps are on the cap and so on, and then first of all notice that because this is just gamma mod conjugation, and so one more way to think of this is the center. Sorry, this would be the center of the group algebra of gamma, because we want some class functions on elements of gamma. And then the cap, this is the thing which will take lambda g to 1 of e, multiplication will be the sum of lambda g1 tends to the sum of lambda g2 to the thing with coefficients, and whereas the coefficient of g will now be sum of rho g of lambda h mu ak, where hk is equal to g of g. And one gets a similar kind of formula for the coproduct, but from this, if we compute, so now if we want to compute the value on some Dumushkin group, like I said, it's enough to compute the values on what does a torus do, and then add in the end the value of what does the, so the torus will be some co-multiplication followed by some multiplication, and if one computes that, you actually get that this is a map which sends a vector into the vector times the sum over all irreducible characters of the group gamma. Take the dimension of each of the characters, if I'm not mistaken, squared, yeah. But each extra factor, each extra tori, extra genus that we add adds an extra factor, and from all of this,
everything that comes on the left of this door, I don't change anything for this computation.
No, but all I want is just to compute the value on a closed thing. So if I want to compute the value on a closed thing, then this is the same as doing the punctured tori, and then adding just a single element, the cap, because I want from empty boundary to empty boundary.
Yeah, but tori can appear several times, yes?
Yes, yes. So each one of these adds an extra factor. So for example, from this you would get that the home from I1 of SG into gamma will be, I think this here I needed some development. But from this you get that this is equal to the size of G to the 2G minus 1, sum over all row and in row to the power of 2 minus 2G. So kind of each of these adds an extra factor, and if you want to compute it for a periodic field, then you also need this extra weird twisted factor, and from this you would get that
This is the size of the set, or what? What's the equality to zero?
it's the size of the set of homomorphisms, yeah. So this Z for a manifold without boundary computes the size of the homomorphisms from pi 1 fit into the group divided by divided by the size of the group. But if you then move it to the other side, then you get a formula for counting the size of the homomorphisms. And then the extra factor that you later get for